Well, starting from our last video, we basically said that the area under the curve, if the curve is above the x-axis and above the area below the curve and between the x-axis, could be expressed as what we call the Riemann integral, which is that summation that we talked about, at least one version of it. In this particular case, the integral from a to b of f of x dx represents the area under the curve. We call that a Riemann integral because we base it on the idea of that Riemann sum. But what we're really doing is we're saying that, okay, if we can evaluate this thing, we can find the area under the curve. Now, it's not always necessary to know what to do with the integral to get this. For example, if we're saying that the area under the curve is the Riemann integral, and we say, all right, let's evaluate something like this one. What's the area under the curve of y equals 2x plus 1 from 0 to 3? Well, the way we're going to do it is that we can just use some basic geometry right here. And you recognize that this is a trapezoid. And in a trapezoid, right, the area could be found as 1/2 the height times base 1 plus base 2. Let's say that's our trapezoid, right? Whatever the sides of our trapezoid look like. Base 1, base 2 are height, right? So the area would be found by taking that half of that altitude times base 1 plus base 2. Well, you can see that this is in fact one of those things where our height is 2, and our bases, based on the function y equals 2x plus 1 at 1, is 3, and at 3, 2 times 3 plus 1 gives us 7, and so its area would be 1/2 of 2, that's that distance from 1 to 3, times 3 plus 7, which is to say an area of 10. So we can just go with some basic geometry to do this if we're lucky enough to get that sort of shape. Consider this one. Let's say that we have the area under the curve y equals 9x, 9 minus square root of 9 minus x squared on the interval from -3 to +3. Well, what shape have we got here? Well, quite clearly, this is a semicircle. This is the equation of a semicircle on the interval in question. I'm just going to color this all in right here. There we go. That's the area that we want to figure out. How do we do it? Well, we can, in this case, go to some basic geometry, right? Our geometry says that the area of a semicircle would be equal to 1/2 times pi r squared, and the radius in this case is 3. So our area could be said to be equal to one half, that's a better way to spell 1/2 times 3 squared, which is to say 9 pi over 2. So we don't always have to know integral rules in order to be able to deal with this, but we can certainly say that when we're representing the area under the curve, we're representing, if the curve is above the x-axis, an area, just like in geometry, only in this case, we're going to involve the antiderivative, as you'll see shortly.